We'll start with grading of cables today. We have seen that the stress in the insulation is maximum at the conductor surface and minimum at the sheath. To avoid the breakdown of the insulation, it is necessary to have uniform distribution of stress all along the insulation. Practically, some methods are used to obtain uniform distribution of stress. The process of obtaining uniform distribution of stress in the insulation of cables is called grading of cables. The unequal distribution of stress has two effects. First one, greater insulation thickness is required, which increases the cost and size. Second one, it may lead to the breakdown of insulation. Hence, the grading of cables is done. There are two methods of grading of cables, which are, the first one is capacitance grading, second one is use of intersheets for grading. Let us discuss these two gradings methods in detail. Coming to capacitance grading. The grading done by using the layers of dielectrics having different permittivities between the core and the sheath. This is called capacitance grading. In intersheath grading, the permittivity of dielectric is same everywhere and the dielectric is said to be homogeneous. But in case of capacitance grading, a composite dielectric is used. You are looking here the diagram. D1 means diameter of the dielectric with permittivity epsilon 1. Capital D is diameter of the dielectric with permittivity epsilon 2. The stress at a point which is at a distance x inversely proportional to the distance x, which is given by Gx q by 2 pi epsilon x. Like that, the stress at any point in the inner dielectric can be found. Similarly, the dielectric stress in the outer dielectric stress is found, and the total voltage will be expressed, and that total voltage, then C is equal to Q by V. You are substituting Q value there, V value there. So the stress is maximum at the surface of the conductor. So G1 max you find. After that, we will find stress is maximum inner surface of dielectric epsilon 2, that is at x is equal to d1 by 2. Then G2 max is equal to Q by pi epsilon naught 2 into d1. Substituting Q in terms of V, we get finally G max, which is written here, that is final relation. If the cable had homogeneous dielectric, then for the same value of D, capital D and G max, the permissible potential difference between core and earth sheath will be like this. So next, coming to intersheath, that is a brief discussion about capacitance grading. Next, let us go to the intersheath grading. In this method of grading, in between the core and the lead sheath, number of metallic sheets are placed, which are called intersheaths. All these intersheaths are maintained at different potential by connecting them to the tappings of the transformer secondary. These potentials are between the core potential and earth potential. Generally, lead is used for these sheets as it is flexible and corrosion resistance, but as its mechanical strength is less. Aluminum also can be used. Aluminum is low weight and mechanically strong, but it is much costlier than lead. Using the intersheaths maintaining a different potential, uniform distribution of stress is obtained in the cables. Consider a cable with core diameter D and overall diameter with lead sheath as D. Let two intersheaths are used having diameter D1 and D2, which are kept at the potentials V1 and V2 respectively. Okay. When we do that derivation, we'll end up with this expression. After that, finally, we will get the relation of G1 max, G2 max, and G3 max, which speaks about the intersheaths. If intersheaths not used, G1 max will be V divided by D by 2 ln D by D. Hence, with intersheath, it gets reduced by factor 1 by 3 into 1 plus alpha square. So this completes the intersheath grading.